Welcome to lesson 2 on interest as part of my financial math series. In this lesson, I'm going to talk about present value, discounting, time value of money, and inflation and taxes relative to interest. So let's start with present value. This is kind of a variation on the various interest formulas. It's kind of working in reverse. You'll see what I mean in a minute. So present value refers to the sum of money which invested now at a given rate of interest will accumulate to a specified amount at a particular future date. So I have an example here. What is the present value of $25,000 3 years from now, assuming 5% interest compounded monthly? In other words, how much money needs to be invested now at 5% interest compounded monthly with no additional investments or withdrawals to have 25,000 in 3 years. So we can write this out here. In terms of compound interest formula, we want to solve for P. So in other words, we want to have 25,000 in 3 years. So that's the 3 here using the compound interest formula. It's compounded monthly, so that's the 12. And then this is the interest rate per month, right? It's the 5% divided by 12. And so we don't know what P is. That's what we're asking. What do you need to start with in order to end up with 25,000? So you basically compute this number here and then divide it into 25,000, and that gives you your answer. In this case, it's 21,524 and 41 cents. So why might you want to do this? Well, maybe there's some car or some present, a wedding present for a child. Maybe you want to help, again, a child was purchasing a house and you know that they're 3 years away. And so you want to have $25,000 then, and you have the possibility of buying a bank certificate of deposit at this under these conditions here. So you could put away 21,524 and 41 cents, and you would know that you're going to have that 25,000 3 years from now. Okay, so in general, we can derive the formula here. Let PV be the present value, so that would be this P basically, and FV be the future value of PV over S compounding periods with interest rate I per compounding period. In terms of the compound interest formula, we have FV equals PV plus 1 plus I to the S. This was the formula we derived earlier for compound interest. This was the principal here, right? PV was the principal, and then this was the amount you would have over this time interval at this interest rate per compounding period. And so you just need to divide this into both sides, and you get the formula for present value. Again, this is for compound interest. You can also compute present value for simple interest and continuous interest, and I have those equations on the next slide. So it's the same idea for simple and continuous interest. You just take the formula you have for a given amount of principal under simple interest, and you divide 1 plus RT on both sides, and you get the present value formula. And you do a similar algebraic manipulation to get the present value under the conditions of continuous interest. Let's talk about discount next. A discount is interest that is taken up out front before you receive the loan money. The simplest way to picture it is in this example here. You borrow $1,000. The lender applies a $100 discount, interest effectively. You actually receive $900 at the beginning of the loan, but you still must repay $1,000 at the end of the loan. So you pay interest on money you never actually had in your hands. Why it matters, the key insight. A discount looks like a 10% rate, $100 on 1,000, but in reality, you're only given $900 and you paid $100 for it. So the effective rate is 100 divided by 900. So it's actually 11.11%. A discount, this is just another way of stating it here. A discount is interest deducted from the loan at the beginning, so you receive less than the amount you must repay. Some intuition here, a quick analogy. Someone says, I'll lend you $1,000, then immediately says, I'll keep $100 as my fee. You walk away with $900, but then you still owe $1,000, which you need to repay at whatever the end of the term of the loan is. Okay, so I'll go over this a few more times on the next several slides, because I know it's a bit different from what you're probably used to in terms of bank loans and interest rates. So we'll go over it a few times. So second try at describing a discount on this slide here. It should line up with what I said on the previous slide, but just different words. Discount is a concept similar to interest. Discount is paid or due at the beginning of a payment period and is calculated on the balance at the end of the period. So the example I gave in your last page, there was just one period, so it's sort of like simple discount. Interest is paid due at the end of a payment period and calculated on the balance at the beginning of the period. There are some cases where the anticipated amount of money owed at the end of the loan is deducted at the start of the loan, i.e. interest paid up front. This is known as discounting a loan, and the rate of discount is represented by the symbol D. So one caution here, you might hear the term discount rate in conjunction with the United States Federal Reserve. That's the amount it charges banks for short-term loans. And that's not what we're talking about here, just to clarify. So I have another example, similar to what we talked about on the previous slide, but a different example. A bank makes a short-term, 9-month, $10,000 loan to Ms. Peoples at a 7% annual discount rate. So the bank deducts 9/12 of your 7%, in other words, 5.25% at the beginning of the loan. That's the discount. And Ms. Peoples receives the $10,000 minus the discount. So she gets $94.75 up front, but she needs to repay $10,000 at the end of 9 months. So the effective interest rate per 9 months is 525 divided by the amount of the money that was actually given to Ms. Peoples. And so that comes to 5.541%. Okay, so let's continue. I'll give you some general formulas now for the discount. So let's look at some formulas. The effective rate of discount, denoted as D, from time t to some later time t hat, is the ratio of the change in value of an investment, known as the amount of discount, to the value at the end of the period, in other words, the time t hat. And so we have it in terms of a formula here. This is the value at the end of the time period, this is at the beginning, and then you divide by the value at the end of the time period. So we saw that in our example, where it was the $10,000. We had the difference from the end of the time period, what you pay back and what you got initially, divided by the value at the end of the time period, $10,000. And that came to the 5.25% for our example. And then I have a chart of it here. So this is the, just maybe put some numbers here. This is sort of like your $10,000. This is the $94.75 that you get, and then the discount, and just using this up here, if you multiply this on both sides, the discount is just the difference between these two numbers, which would be 525 in this particular example here. And then the discount, or the effective rate of discount, I should say, D, is just the number we need to multiply times 10,000 in order to get this difference here. So you get that by this formula here. Okay, so let's continue. I have a little bit more on this topic. I want to apply the formula from the previous slide to compound interest and simple interest. So we're going to take we're going to compute, I should say, the effective rate of discount, just going from one period to the next. So from period n minus 1 to period n in terms of the compounding periods. So this is the value at the end of the nth period, and this is the value at the end of the n minus 1 period, and you divide by the value at the end of the nth period. Then we plug in the formulas for compound interest, which I have in here now. And if we divide all the terms here by this term here, the p times 1 plus I n minus 1, then of course it divides into itself once, and you get the minus 1 here. When you divide it into this, you're just left with 1 plus I. And the same when you divide it into the bottom, you have 1 plus I. The minus 1 and the 1 cancel, and you get I over 1 plus I. So if we solve for I, we can have that in terms of the effective rate of discount, if you like, and that would be this expression here. Again, this is just in the case of compound interest. In the case of simple interest, the effective rate of discount depends on both the duration of the loan, T, and the annual interest rate, R. Since there's no compounding, there's only one repayment period, which starts at time 0 and ends at time T when you have to pay the loan back. The formula for effective rate of discount in this case is as follows. So this is the amount, the principal. This is the amount of simple interest plus the principal at the end of time t. Then you divide by that. And then you notice this, when you multiply this out, you get a p plus PRT. But the p's cancel out, and then you can also divide by p here. And then you get this expression here. So I have an example using this. What is the effective rate of discount for a simple interest discount loan of $10,000 for 18 months at 10% per annum? So we're given R is 0.1, that's our 10%. T is 1.5, that's the number of years, 1.5, 18 months. And then the discount, we can use this formula here. So R times T, so 0.1 times 1.5, that's 0.15. Then on the bottom you just have 1 plus 0.15, so you get 13.0435. That's our effective rate of discount for this particular example. Note that the discount is 13.0435% of the final value. So it's, if you take this percentage times the final value, you get 1,500. So the borrower receives the 11,500 minus the discount. So the borrower receives $10,000, but he or she needs to pay back 11,500 at the end of the year and a half. So in summary, an 18-month loan of 11,500 at a discount rate of 13.0435% will result in the borrower getting $10,000 at the beginning of the loan with the obligation to pay back $11,500 in 18 months. You can also use discount rate to accumulate money. It's a bit unusual, but I'll mention it here just to give us some practice in working with discounts. So looking at the chart here on the bottom, you start with x0 and you end up with x1, which is more than x0, and it's the way it happens is you're kind of promised this amount of money, and you give or pledge or contribute an amount that's discounted. So it's x1 minus some discount times x1, and you can solve for x1. It's just factor it out, and then you multiply both sides by 1 minus d to the negative 1 power, and you get x1. So for example, if d is 0.01, this is 0.99, and then when you take the reciprocal, it's a little bit bigger than 1. So you get slightly more than what you had here. And then you can do the same thing going from here to here, which I've written out. You let x1 be x2 minus some discount times x2. So in other words, this amount of money here, when contributed, gives you this much, slightly more at the end of the period. And you can solve this. You just factor out an x sub 2, and then multiply both sides by 1 minus d to the minus 1 power. And you get this here. But we already solved for x1 in terms of x0, so you can plug that into here. And you get x2 equals x0 times 1 minus d to the minus 2. And then you can continue that for the third and the fourth and so on. And finally you get to the nth period, and xn equals x0 times 1 minus d to the minus n power. So if you contribute 0 here, you would end up with this much money using these discounts at each point along the path here. So I'll show you an example or a few examples on the next slide. For example, what amount must be invested at a discount rate of 0.45% per month to have $50,000 at the end of 10 years under a monthly compound discount approach? What we talked about on the previous slide. So we're given the effective discount rate, which in terms of a decimal is 0.0045, and the number of periods is 10 years and monthly, so it would be 10 times 12, 120. And we're looking for the initial amount so that at the end of the period of 10 years, we have 50,000. So we use our formula here. We're given x0, d, and n. So we just plug that into our formula here, I guess, the first line. And we multiply both sides by 1 minus 0.0045 to the 120th power. So it cancels on this side, and then you get it on multiply times 50,000. You can do the subtraction and then use a calculator to raise it to the 120th power, and you get $29,101.93. So if you start with this and you use this discounting scheme, you would have $50,000 in 10 years at this rate here, discount rate here, under monthly compounding. So let's look at another example. Consider a discounted 5-year loan at a discount rate of 0.4% per month, where the loanee initially receives $100,000 from a bank. And the question is, what is the actual size of the loan, i.e. the amount of money to be paid back to the loaner at the end of 5 years? So here we're given D is 0.004. The N is 5 years times 12, since we're doing monthly compounding, and that's 60. And we're told that the loan is 100,000, so that's the x sub 0. And we're looking for x60, the final amount here. how much has to be paid back. So you have 100,000 for x0, 1 minus 0.004 to the minus 60th. You're using this equation here. And then you just put this into a calculator. And so it's $127,186.11. So in other words, a discounted loan in the amount of $127,186.11 is requested. The discount amount is this sum $27,186.11. That's deducted from the loan at the beginning. So the loanee receives $100,000, and then he or she needs to pay back this $127,186.11 at the end of the period. If you recall a few slides back, we computed the equivalent interest rate when you do compounding using this discounting approach here. So our D in this, for this example, was 0.004. If we plug that into our formula, then we have this slightly bigger than 0.004. And if you compound that monthly for 60 months, and you start with 100,000, and so that's this formula here, you get exactly the amount of the loan, just sort of a double check. On this slide, I have a diagram which I showed you at the end of the very first lesson. And at the time I said, if you don't understand it, don't worry, we'll get back to it. So here we are. I think now you've probably seen enough to understand this. There was a typo when I first presented it. I believe I had x plus in, and it should be x plus 1 plus in, as I've shown here. So this is correct. So the idea is that you can take a particular date and time and work forward or backwards to see what how much money you have after end periods, or what you need before end time periods to get to this. So let's look forward first. If you start with the principal of x, then you can just use our different simple, compound, or continuous interest formulas to see how much this is worth after n time periods. And you can see here for simple, it's this amount. For compound, it's this amount. And for continuous, it's this amount. And you could also work backwards. You could ask, how much money do you need n time periods in the past in order to have x dollars at the end of these n periods, depending on different interest rates and approaches. So I have one example here where it's compounding. So if you started with x times 1 plus I to the minus n dollars, and you had n time periods with interest rate I per time period, then this would be your principal, and you would multiply this times your 1 plus I to the n, and that would give you x. And you can do a similar thing for or simple, but I showed here for continuous. So this would be your principal, and then you have n time periods with an interest rate of I per time period, and you do continuous compounding. Then this is your starting principal, and you put that into the formula for continuous interest. And you have this here, and of course these multiply, and you just give you 1. And so you have x dollars. Okay, so I'll give you a few examples of this, but this is an important concept to be able to work back and forth from a given amount of money at a given date. Consider a personal loan of $5,000 between friends that is due at the end of a 3-year period. So the one friend doesn't need to pay it back until the end of 3 years, and there's no interest if he or she pays it back on time. To allow flexibility, they also agree that an early or late repayment will be adjusted using a nominal annual interest rate of 6% compounded monthly. Determine an equivalent amount of debt due in 1 year. In other words, if the loan is paid back 2 years early, and in 5 years, where it's paid back 2 years late. So let's look at this case first. We select the focal date, and I'm referring back to the diagram from the last slide, to be when the debt is due, in other words, in 3 years. The equivalent value of the debt 2 years before the focal date, i.e. 1 year from present, is 5,000 times 1 plus our 6% divided by 12, since it's compounded monthly, and this is the number of compounding periods. So in other words, if the one friend who loaned the money pays it back early after just 1 year, then this amount of money would accumulate to $5,000 in the following 2 years. So the person providing the loan is kind of giving a break to his or her friend in this case, if they pay it back early. And if they come back late after 2 years, then this is a little bit more what we're accustomed to. Then it would just be the 5,000, and then the interest would be charged for 2 years. So it would be 5,635.80. So in this case, the debt is later than the agreed repayment time, which we assume to be the focal date in the calculations. As a second example, assume Mr. Jasper owes Ms. Dubois $1,000 in 6 months and another $1,500 in 2 years. What single payment in the present will liquidate these debts if both parties agree money is worth 3% compounded monthly? Then I'll ask you the same question if the debt is paid back in 1 year. So in the first case, both of these debts are paid back early, and we need to compute the value of the $1,000 6 months prior. So it would be this formula here. You notice there's -6, and this is the interest rate, and this, if you divide by 12, you get the rate per month. And then the second loan is paid back 2 years early, so you use this formula here. When you add them, you get $2397.88. Then the second question, one loan is paid back late, right? Because he's paying back in a year, and he's missing the 6 month for this one here. So that would be 1,000, and then the interest accrued over the 6 months. So that would be this amount. And then you're still paying the second loan back a year early. So you have a -12 here, and together it's still a little bit less than the 2,500, since this one kind of offset the additional amount of money being paid here. A common technique in financial mathematics is to replace one set of payments with an equivalent set under a given interest rate model. Two payment streams are said to be equivalent if they have the same value at a chosen date. This is the focal date I had been talking about. Under a fixed interest rate scheme, equivalence at one date implies equivalence at all dates. So let's see if we can use this idea to solve a fairly tricky problem. A business borrows $100,000 today. Interest accrues at a nominal annual rate of 4% compounded monthly. The loan is to be repaid in 3 equal payments at the end of 4 months, 7 months, 11 months. So the key word here is equal payments over these 3 periods, together with a final payment of $20,000. So we know what the final payment is at the end of 13 months, but we don't know what these 3 are here. And it's not 80,000 divided by 3, because you have to take into account the fact that you have to pay the interest off, whatever is accumulated at the end of 4 months, whatever is accumulated at the end of 7, and the end of 11 months. And at the same time, you want these 3 payments to be the same. So it's, as I say, it's a fairly tricky problem, but we can solve it. It depends on picking a focal date, and as we'll see, any focal date will work, but I'll give you a chance to try this, then I'll show you the solution on the next slide. So let's look at a solution to our problem. Let X denote the amount of each of the three equal payments. We need to select the focal date. Any date will do, but we're going to pick 7 months as the focal date. At the focal date, the accumulated value of the payments, in other words, present value, must equal the accumulated value or present value of the original loan. So we need to look at 5 different values. The 4 payments at 7 months, and then the accumulated amount of the loan. So the accumulated amount of the loan is 100,000 times the compounded interest formula here, 1 plus I to the 7th. So this is the principal, and this is compounded. I is 0.04 divided by 12 since we're compounding monthly. And 7 here is because it's 7 months into the after the loan is made. Then the first payment is 4 months. It's supposed to be made at 4 months, but it's being made at 7 months, so it's 3 months late. So that would be X times 1 plus I cubed. And then the second payment is on time, so that's just X. Then the third payment is made at month 7, but it wasn't due until 11, so that's actually discounted. That would be X times 1 plus I to the minus 4. And then the $20,000 payment, again, is made 6 months early because it wasn't due until month 13. So that's 20,000 times 1 plus I to the minus 6. So we need to plug in I for here, here, and here, and then add these together first. And we get 2.99681 times X from these 3 terms. Then this term here, we know the exact value because we know what the payment is. It's this number here. That needs to equal this. And then we subtract the 19,604.63 from this number here, and then divide by this, and we get X. So it's roughly 27,613 in some odd cents. Okay, so if you make this amount at these 3 periods, these 3 intervals, 4, 7, and 11, and then the $20,000 at the end, that covers the loan properly. So just to illustrate that this focal date can be chosen at any date by our equivalence principle from the last slide, I did it a second time, and I chose month 13 as the focal date. So in that case, the first payment is 9 months late, so you have 1 plus I times to the 9th power times X. Then the second payment is 6 months late, so you have a 6 here. The third payment, 11, that's 2 months late, and then the 20,000 is on time, so we just add that in directly. Then you compute this, and you get some value times X plus 20,000. You subtract that from this quantity here. I didn't show all the details, but if you go through all that calculation, similar to what we did up here, you're going to get the same number. So this confirms, at least via one example, under a consistent interest rate model, equivalent payment streams have the same value at any focal date. Okay, so kind of complicated. You probably want to look at this a second time to absorb it, but as we see here, it does check out. And you might want to try yet another focal date, maybe say 11 months, and see if you get the same number, which you should. So the previous example might have been a bit confusing. It made me think quite a bit too. So you're probably asking, well, what exactly is X in terms of the repayment? And what might help clarify a little bit is this table here. I tried to show with some help from artificial intelligence that did this computation, what happens at the end of these payment periods. So you start out with a balance, you're given $100,000, and that's how no payment interest is accrued yet. And then at the end of 4 months, you have an interest at this, 4% per month compounded. So you owe this much money in addition to you still owe the total 100,000. So this is how much is owed. And then we figured out these payments here. So the trick is that you're paying the interest, and then whatever else from this amount is principal paid back. So you do that, your principal is reduced to this amount here, which I'm showing at the starting point. And then for these 3 months, this amount accrues this much interest. So it's smaller than the original amount because you pay back some principal, but you have this much interest, so you need to add it to this number here to get this here. And then again, you do the fixed payment, X, and then whatever is left after this amount is how much principal you paid back. And so again, you reduce the principal, and then that's the starting point for this next period, which is 4 months now. So you accrue this much more interest. You add it to this, so you now owe this much now at the end of the 11th month. You pay the fixed amount. Whatever is left after you subtract this is principal paid. So you're down to this amount here. And then for 2 months, this accumulates another 132.67, and then you pay it off. And there was some rounding. It was off by a penny when the artificial intelligence did it, but this would be 20,000. And so at that point you've paid the interest as well as almost exactly the 20,000, except for this rounding mistake, and you're down to 0 here. Okay, so I hope this helps clarify a little bit what this X actually means. It's a combination of principal paid back and paying back whatever interest accrued over 4 months, and then over the next 3 months, and then over the next 4 months, based on how much was still left in balance at the end of each one of these periods. On this slide and the next, I want to talk about the impact of inflation and taxes on interest. So we have a few examples here. At the beginning of a given period of time, assume that you have $1 and the inflation rate is 3% for that period. An item that costs $1 at the beginning of the period will cost $1.03 at the end of the period. Your $1 at the end of the period can only purchase 1 divided by 1.03, or 0.97, in other words 97 cents of what it could have at the beginning of the period. So the effective simple interest rate is minus 3%. In other words, 0.97 from 1. It gives you the number here. Another way to view this is to ask, what is the future value of $1 under minus 3% simple interest for, I said 1 year here, but I guess I should have said whatever the time period is. Let's just say it's a year, make it more concrete. So we would have our future value formula for simple interest. We put in the minus 0.03 here for R, and T is 1, and then we get 0.97. I just mentioned what the different values are down here again. So, however, if you invested $1 at 5% interest at the beginning of the period, you would have $1.05, which could be used to purchase this number here, 1.05 divided by 1.03, or $1.01, almost $1.02, right? 1.0194 of what you could have at the beginning of the period was $1. So the real return, given both the inflation and the interest, is 1.94%. So another way to look at this is, say at the beginning of 1 year, a candy bar cost $1. Also at the beginning of the year, you invest $1 at 5% simple interest. Over the course of the year, inflation is 3%. So we're using the same numbers from up here. At the end of the year, you have your $1.05, and you want to know how many candy bars you can now buy. Call this quantity X. So due to inflation, the candy bar now costs $0.03. So we have the task of solving the equation. 1.05 equals 1.03 times X. X is the number of candy bars you can purchase, and if you just divide on both sides by 0.103, you get the number we had up here, and that gives you the same result that we had up here. So this was just another way of looking at it. We can state this generally. If you have a given interest rate and a given amount of inflation, we can compute the effective increase or decrease in your buying power, and I'll do that on the next slide. In general, if the interest rate for a given period is I, and the inflation rate is R sub inf, just to give it a name, the real rate of return, i.e. the interest adjusted for inflation, is this number here. This is known as Fisher's equation. So we did this for a particular problem on the previous slide where we had the candy bar example. So the interest rate was 0.03 and the interest rate was 0.05 and the inflation was 0.03. And so we got our number, and then we subtract the 1 just to get the interest amount, or the effect, I should say, the adjusted interest amount. We could also figure in taxes if you like. So if there is a tax rate of I sub t at the end of the year, or a given period, let's just stick with the given period, the effective interest rate becomes I sub t times whatever your interest is, and this gives a modified real rate of return with taxes considered. So it's almost the same as this here, except you have your interest rate and then you lose this amount I sub t. So what you retain from your interest is the 1 minus that. And so, for example, if the tax is 3%, then you would retain 97% of the increase you're getting from your interest. So I have an example here. Excuse me. So returning to the previous problem where we had 5% simple interest, 3% rate of inflation, and assuming a tax rate of 20%. So this is what I was talking about here. So you retain 80% of your 5% simple interest. So you have to adjust that up here. And then you get 1.04 divided by 1.03, and then you subtract 1 just to get your effective interest rate, taking into account inflation and taxes, as well as the interest you're earning. On the next few slides, I have exercises that pertain to this lesson and also the previous lesson, part 1 of interest. So you need to look back there for, in some cases. So I'm not going to give you the answers for the most part. I do have quite a few hints, so we'll just talk through these quickly and then leave you to solve the problems. So the first one is determine the value of a simple interest investment of $10,000 at 3% annual interest rate over a period of 2 years and 7 months. And what would be the value of the investment if you had daily compounding instead? Okay, so simple interest and daily compounding. And you can use the calculator I talked about in the previous lesson. That was a Python program, if you recall, and I made the code available. Or you could try doing it by hand, or you could just look it up, a calculator on the internet, and you should be able to solve this one. The second one isn't much harder, it's just the numbers are bigger. Country A is doing a favor to country B. It loans the country B $1 billion over 100 years at an annual interest rate of 6%. So compute the amount of interest paid back to country A under the assumption of yearly compound interest. So just compounding the 6% once a year. Daily compounded interest every day, basically over the 100 years, and then continuous compounding. And to be clear, the loan is paid back in full only at the end of the 100-year period. So country A is sort of maybe not doing a favor to country B. It's assuming this is a good bet if the inflation is more than 6% over the 100 years. And if inflation is very low over that period, then I guess country A makes out better in that case. So you can use my calculator again for this, and I'll just mention that the amount you get for the daily compounded and continuous are very close, but the yearly compounding is quite a bit less than either one of these two. Then we have a third question on this slide. Mr. Wimple buys a diamond for investment purposes at $55,000. He holds the diamond for 5 years, 6 months, and then sells for $100,000. What is the effective interest rate per year? So, assuming simple interest. So you just take the difference here, which is $45,000. You divide by $55,000, and you'll get your interest rate over the entire 5.5 years. So you have to divide that by 5.5, and you get 14.876%. Then I asked the second question. For comparison, what would the effective interest rate if monthly compounding was assumed? So let's say Mr. Wimple did the same thing, but he invested the money instead of buying this diamond. So you have $100,000 is sort of the final amount, and you started with $55,000, and you have monthly compounding over 5.5, so T would be 5.5. I didn't plug it in here. I should have plugged it in here. So you have 5.5 plugged in for T here times 12. And so you know everything in this equation except for R. You take the natural log on both sides and then apply some algebra to isolate R. And if you solve for R, you get 10.9191% approximately. So it's a smaller amount, a smaller interest rate would be needed to attain the $100,000 in this investment in the case of monthly compounding. Problem number 4. Given a nominal yearly interest rate of R, compute the effective annual interest rate under the assumption of continuous compounding between times T and T hat. So this is from interest part 1. We had this formula here for effective interest rate. This was the value at time T, which we'll just call that P. And this is the value at time T hat. And so we would use the continuous interest formula to figure that out, given that you had P amount of money when you start it, and then the length of time that transpired was T hat minus T. Then you just cancel out the P's and you get this here. So this is the effective interest rate over the entire time period. And to get the effective annual interest rate, we just need to divide by T hat minus T into this thing here. So I pretty much gave you the answer on this one. You may want to plug in some specific numbers just to try this out. What nominal annual interest rate R is required to quadruple an initial amount in 20 years with monthly compounding? Then the same question for continuous compounding. So people often ask these questions because you may put money in the bank and you want to know, I'm 20 years old now, when I'm 40, what interest rate would I need to double or in this case quadruple the money? I'm not 20, by the way, but just giving you an example. So for the first question, we want to know, we started with principal P, and it's compounded monthly. So we don't know what R is, but it's for 20 years. So 12 months times 20 is 240. So that's the number of periods. And we want to know for what R does this actually equal 4 times quadruple, in other words, the principal. So we to get R, we just solve this. We would need to take the natural log on both sides, or actually we could divide the P out first and then take the natural logarithm on both sides and then solve for R, and we'll get 6.9515%. For the second question, it's similar, except we put in the formula for continuous compounding. So it would be this here, the time 20 times the R, which we don't know, and we solve, again, we would cancel out the P's, take the natural log on both sides, and then solve for R. And we need a slightly smaller interest rate to quadruple our money over 20 years. But that's pretty good, right? The stock market typically makes more than that per year on average. So over 20 years, you would expect to at least quadruple your money if you invested it in a broad-based fund like an S&P 500 fund. And again, that's just, don't take my financial advice. I'm not an expert, but I'm just giving you some numbers based on historical averages. Okay, so we have 2 more questions, which I'll get to on the next slide. Problem number 6. A rich uncle leaves $5 million to 3 heirs, all nieces. Each niece is to receive an equal amount of money when she turns 21, which will be 12 months, 27 months, and 47 months from the time the will is executed. In the meantime, the money is invested at a nominal annual interest rate of 6% compounded monthly. How much money is each niece to receive? So we take this 0.06 and divide by 12, we get 0.005. Just to tell you that up front before I set up the problem. So we'll take the focal date to be the date the will is executed, in which case this stream, the money going out, is $5 million at the focal date. And then what's the present value of the amount of money to the 3 nieces at that same time? So you have to discount it by 12 months for the first, the oldest niece, and then discount it for 27 months for the next niece, and discount the amount for 43 months for the youngest niece. And then these present values should equal the 5 million, since we've computed these all at the same focal date, basically the time the will is executed. Okay, so what you need to do is compute these numbers with a calculator, and then add them together and then divide into 5 million to find X. Then the last problem in this sequence of exercises, and basically the end of this lesson, it also involves this type of calculations. And we'll see this again when we talk about annuities, but this kind of gives you a preview of what we'll be talking about. So given a debt Q at time 0, repaid by n equal payments of amount X made at the end of each period, with periodic interest rate I, determine X. So similar to this, we're going to take the focal date being time 0, and so we have Q, that's like our 5 million, we have Q, and then we have these n equal payments at these periods. So one period after the present value for the first period is this here, discounted. Then second period is this amount discounted, and then all the way to the nth period discounted by n time periods. We can use the formula for the sum of a geometric series. I talked about that earlier on, one of the previous lessons. That's a known formula. And then you solve for X, and this would be the answer. Again, we'll see this in the next set of lectures that I'm going to have on annuities. Okay, so that's the end of this lesson. It was quite long, almost an hour. And if you like this, don't forget to give it a thumbs up and stay tuned for additional lessons.